Alright, let's look at question 16. In the diagram, DC is a diameter, so that tells me that DC cuts through the center of the circle, and the tangent to the circle at point A, so this is a tangent is a line that touches the circle at one point, it meets DC produced, so DC produced means DC and then you produce, you continue a straight line and you produce a bit more, so it meets DC produced at B. Right, this tangent meets DC produced at B. They meet at B. And given that the radius of this circle is 20 cm, so let me just label that quickly. So this is 20. And that also tells me this is 20. And that also tells me that this is 20. I just like to label it in case I need it later. And it tells me that CB is 20 cm as well, so I should label that. CB is 20 cm. And the question, part A, says find angle AOC in radians. So where is angle AOC? So that is my angle. Just a question. What is this angle? And so let's try to analyze. It doesn't look that straightforward at first. I mean, they gave me a ton of like lengths, but I don't know anything about the angles, right? They didn't give me like, oh, this is how many degrees or how many radians. But let me see if I can deduce based on the geometry, based on the shapes. So I can say that this is a tangent that meets a circle, and then you draw, wherever it meets the circle, you draw a straight line to the center. We know that the tangent that is connected to the radius of a circle will form 90 degrees. So we know that that is 90 degrees. Do we know anything else? Doesn't seem like it. So let's try to construct this triangle AOB, and we say that this is the angle we are looking for. And let's just fill in what we know. This is 20, and since this is 20 plus 20 cm, so this whole thing is 40 cm. It's 40 cm. All right. And we know that this is 90 degrees. What comes to mind? What comes to mind? Well, what comes to mind is sine rule. If I can use this angle and this length, and if I can find this length and this angle, I can apply the sine rule. Can I do that? Can I find this length? This is a 90 degree triangle. So yes, I can use Pythagoras theorem. So by Pythagoras theorem, it tells me that 20 square plus AB square equals to 40 square. So I can say AB square is simply 40 square minus 20 square. AB square is 1,200. And so I can say that AB is simply square root 1,200. And I'm just going to leave my answer like this for now because I don't want to round it up or down because I'm still going to use it for other calculations. So I'm just going to leave it as square root 1,200. And then the next thing I'm going to do is I'm going to apply sine rule. So I'm going to say that the sine of this angle divided by this length equals to the sine of this angle divided by this length. If I'm going to highlight it for you, if it helps, the sine of this angle divided by this length equals to the sine of this angle divided by this length. And so let's write it out. Sine of that angle, the 90 degrees, over 40 is actually equal, applying sine rule, sine of whatever angle that is, which is actually AOC, that's the angle we're looking for, over this length, 1,000, square root 1,200. And now we can solve. So we can say that we multiply square root 1,200 over, so we can say that sine 90 over 40 times square root 1,200 equals to sine angle AOC. And we can find this is equal to, if you key into a calculator, it will give you a nice result. And then we can say angle AOC is therefore sine inverse of this, which is pi over 3, yep, radians. And of course, you could have gotten 60 degrees here. If you got 60 degrees, then you convert 60 degrees to radians, right? So alternatively, you could have found, if you use your calculator in degree mode, that this will give you 60 degrees, and then you would say you would convert that to pi over 3 radians. And how you convert it, previous videos will show you very clearly. I'll just go through very quickly here. So I get to 1 degree. And then I get to 60 degrees. There you go. All right. Now that seemed like quite a lot of work, really, for part A. Part B is actually more straightforward, B, C, and D. The area of sector, find the area of sector AOC and the area of triangle AOB. So to find the area of triangle AOB, it's just this. Actually, it's pretty straightforward. We have half times base times height. We know this is the height because it's 90 degrees. So let's just do that. So all of this was really part A. Let's do part B over here. So we look at triangle AOB. We can say that the area is half times my base, which was found, times my height. And that equals to 346.41 cm square. This is in 5SF. I'm just going to leave it there for now. If I want 3SF, I would say maybe 246. Okay, and then now I want to find the area of the sector AOC. So it's not the triangle, okay? It says sector, so I'm trying to find really this entire sector, this area, AOC. The good news is that I already found this mystery angle. It's no longer a mystery. It's now found to be pi over 3, right? We found it over here in part A. And since pi over 3, I can easily find the area of the sector using the formula. I can say that the area of the sector AOC is simply given by half r squared theta, which is half, my r is 20, so 20 squared, theta is pi over 3. Key that in, and I'll get 209.4 for 5SF and 209 3SF. There we go. Okay, now let's look area of shaded region ABC. So where are we looking at? ABC, but this is the shaded region. Oh, that's good news because we just found the area of the sector AOC, the blue one, and we already found the area of the triangle AOB, which is this one. And so all we have to do for part C is simply take the area of this triangle and we subtract away, if you can see, this sector, and what is left is the shaded region. So we just take, now you can see why I left it in 5SF. You can take this, subtract away this. And so that really leaves us with the working 346.41, right, over here. Subtract away this, 209.44. And the area of the shaded region is 136.97, and now I put it to 3SF. There we go. Alright, for the last part of this question, 16D, it says, can you find the area of the segment which is inside triangle ABC? So let's look, triangle ABC. Oh, it's a triangle, so that's why they drew this dotted line here as well. So this is my triangle, ABC. And if ask you to find the area of the segment inside, so what it's asking for, just a quick recall, if you have some kind of circle and you split it like this, you draw from the circumference to the circumference, you actually split it into two segments, where this is the major segment and this is the minor segment. So in this case, where is the segment inside this triangle ABC? And so, which is the segment? Let's look at triangle ABC. And you can see that this line actually splits the circle into two segments, where this, I'm just going to use a different color now. Let me use green. And this is the minor segment. And this, if I can use maybe pink, is the major segment. So really, the area of the segment inside the triangle is asking you to find this area, because this is the area that's inside this ABC triangle. And how can we find it? Well, we just found the area of the shaded region ABC, this shaded region. If we can find the area of this triangle, we can subtract away this area of the shaded region and we can find the green area, right? So let's just try to get that to work. And so let's see. I'll do my working on the left here, D. Okay, so we have ABC. And then we are trying to find this area. And the area of the shaded region we've already found. Okay, so let's try to find the area of ABC first. The first thing is we've seen is that, okay, can I find this angle? Am I able to find this angle? I see that this is pi over 3, which, if you're not comfortable with that, is actually 60 degrees. And I also know that this is a radius, and this is a radius. That means this triangle is an isosceles triangle because this and this are both of the same length. That means this angle must equal this angle. So let's try to find that. To do just a side working, to find the angle, I would say, okay, angle OAC, let me write it here. Angle OAC is equals to 180 minus 60 degrees, and I divide by 2, right? OAC is basically 180 minus away the 60 degrees, and I divide by 2. And voila, you actually see that gives you 60 degrees as well. That means both angles are 60 degrees. That means this is actually an equilateral triangle. So this is also 60, and this is also 60. And that is helpful because it means that this white angle is therefore 180 minus 60 degrees, which is 120 degrees. So I can come here and say, okay, this angle, maybe I'll use a different color. This angle here is 120 degrees. And do we know any of the lengths? Yes, we know that this is, we do know that this is 20 cm. And if you analyze here, since we stated that all the angles, we found that all the angles are the same, that means all the sides are the same. That's an equilateral triangle. So if this is 20 cm, right, and this is 20 cm, then this must also be 20 cm because it's an equilateral triangle. And so that's very helpful because we can come here and say that this is also 20 cm. And you can see where I'm going. I can find the area of the triangle, therefore, area of triangle ABC is therefore, I can find half times A times B times sine C. And that gives me 173.21 cm square. This is my 5SF answer, because we're not done, because we're supposed to find, we only found this area, we're supposed to find this small area, but if you look, we already found the shaded region, right? We already found this shaded region, which was, if I take a look, 136.97 over here. So yeah, we can just say my area, my desired area, therefore, the segment, right? This segment is therefore 173.21, and I subtract away 136.97, and that gives me 36.2 cm square in 3SF. And there you go.